have that that want to do the same thing. Now the idea is that you want to be identified. So by just replacing the actual making for the being identified, right? So actually is morphing attack. So if you look at this one, let's assume that it Now, why does more and so becomes a more practical and you know, but but what I should Okay. What happened? Correct.
That I have a new database which has a multiple way of mock quiz. Right? So here, if you look at that one, so if I'm going to create the image of these two people, okay, they both look very similar in the cosine space or whatever the distance that you're using, and then I can select that, right? By doing some simple processing, you can plug it into any of the face recognition system, right? Any of the face morphing system. For the time being, just assume that these are different kind of morphing techniques, A, B, C, D. And there are different techniques based on different approaches. So what it showed, or what it showed in this work, is that by doing that simple selection of the pair, the attack strength increased. You see the attack strength here. For a random attack, the attack was only 25%, less than 25%. Now, by doing some simple selection, the attack increased to approximately 45%. Right? So the graphs kind of moved up upwards. And then even better is in this case, right? You see here for the deep phase-based systems, it goes quite up for this kind of system which is based on MAC phase. Okay? So the idea here is that by selection of the pair, you can create better attack. Now, to just also touch upon the aspect of generative adversarial networks. You remember we spoke about this GAN sampling, GAN-based image generation. It's exactly the same case here, right? So I have two images, and then I can extract the encoding from them, the latent space, which is typically the feature space. And then once I extract the feature space that is here, L1 and L2, these are two coming from two different GAN networks. Oh, sorry, we need to move the points. Here. So now you see that since it is two vectors, A and B, I can add them, right? I can add them A plus B divided by 2, or I can say, okay, 0.2 times A plus 0.8 times B divided by 2. So I do that. And then I have a network which can recreate the image back. So it is recreating the image back up here. Okay. So what am I doing? I'm taking two images, I'm merging them using generative adversarial network and then recreating the final image here. And of course, in case you can also use this image, but then you see that it doesn't look very similar to most of the people. So then what do? You have the identity loss, which is in arc phase, which is in cost phase that we looked upon on Friday. So you insert it back and then make sure that the loss function is respecting the identity. Right? So when I do that, I get a better image, which is again completely based on camera. So here you see some images, sample images. These are subject A and subject B. Now, when I'm merging them, you see that the image is kind of better. So this looks more like this person. Also, at the same time, it has some properties of this person, right? So what does this enable me? Now, this enables me to creation of large scale database. So what I need to do is that I don't have to do so much of manual processing. I don't have to ask you to sit in front of computer for next 20 hours. You simply put in a database of millions of images and you pick random images from that and then create this, use this network, and then you have a bunch of images. So for instance, here, you might see some how it works, right? Even without touching anything, you can see just by clicking two buttons, I'm able to generate this whole face symbol. And since it is generating a number of images, I can pick any number of any particular image that I want. Okay. If you closely paid attention to the previous image, I told you that it was giving good image, but at the same time, it was not giving optimal images. So what can I do? I iteratively go back and then start telling, okay, whatever the problem was in the previous case, try to make it better. And in this case, the use of diffusion process. The most of the pipeline remains very similar, except the idea that, okay, if I can generate a number of different combinations of the images, I can pick the best among them. How do I choose the best among them? So you have the diffusion process to generate all these samples, and then I have a decoder. With the decoder, I can create number of images, and with all these images, I can see how much of the ID is still retained. If the identity information of the two people are not remained or is not retained, I can simply eliminate that one. Make sense? So we are trying to build it up from landmark based to generative adversarial, now generative adversarial to diffusion based modeling here.
So ideal square, just like calculate the losses of those two images.
ID, this ID, right?
Yes.
This ID is the identity. So identity information is nothing but how similar your face looks to my face.
Is what loss is.
It's typically a loss function, right? It's a loss function, yeah. So it's nothing but the difference between the, let's assume in the simplest terms, it's the difference between the face recognition vectors of this versus this. Two vectors, right? So identity information. What is identity information? It's nothing but the information extracted from a deep learning network.
Feature vector.
Feature vector, exactly. Yeah. And that feature vector can be anything. It could be on the best model, it could be something very trivial like a FRS model. Yeah. Okay, so now here, it's also, you can see that in this case, this was the previous results. And here you see there is a bit of a change in the hairstyle, right? When I shared the slides, you can take a look at that. But now here in this case, it's retaining the structure a bit more nicer. So the face structure is very similar to this person. And at the same time, the obvious artifacts that you could see on the top part is now eliminated. Also, those of you who are interested in solving another problem, if you look very closely, do you see a small spot here? Yeah, so that spot is still existing, right? So it is coming from the gun network that you spoke before. So you can try to improve that one. So it becomes very good.
So that spot is feature or the problem in that network?
It's a problem with the network. It's the artifact, right? Because of the way the.
It's not a feature of.
It's not the feature change. Now, if I give it to a police officer and if he knows that this kind of network generate that, he will be able to spot it very immediately.
It could work like feature too.
It can be used as a feature to detect it, but as an attacker, you want it to be eliminated. So if you are thinking from the ethical hacking perspective, you want to get rid of that spot. Okay. Okay, so that's just winded up a bit by diffusion network. Again, in the diffusion network, it is even more easier. So you have a sample on the left side and sample on the right side, very high quality images, right? So if I'm taking the image of left and right, and then I'm telling, okay, put it 5%, 7%, 8%, and so on, you see that how the face changes here, right? So now it has the appearance of that person, but I could also flip it and say, give me the appearance of this person. So I keep the background of that person, only the face changes from this particular person. So what is the idea here? The idea here is that this was a PhD that was recently defended last year. In his work, what he did was he said all the features in the face recognition space have to be in a similar domain. So if I consider like a sphere and I put all the features onto that, two of them should be very close if it is from the same person, right? So that means if I look at the embedding, now again, everything goes back to embedding, right? So I have the embedding from here, and I put it onto a, if I assume a uniform spherical space, they should be lying in a equidistant. That means that they're both in the same distance. And then I can pick those samples, and then I can put them into the condition, and then I can say, now generate me a new face, a face uniform. Okay. Now here in this case, you can see how the appearance also improves. Look at this particular image. Now this person looks very simulated, very synthetic, right? But now if I look at the image here, it has very strong appearance of this person, while it also has the features of this person. So it's incremental like this. So every time I come back with such a new method, what I need to do is I need to go back and recreate that graph I showed you. I showed the graph with number of dots. Yeah. And then you want the images to be in the upper spot. So as long as you achieve that, then your attack is much stronger. Okay, so this is for attacking, right? So how do I detect it? So I can detect it using two different approaches. The first approach is what is called as single image morphing attack detection. And the second one is called as differential image morphing attack detection. Single image morphing attack detection, when does it work? I go to a passport office, or I just upload a passport image into the system, and they don't have any other reference image. Right? So they just have to make a decision on that one image that is given. They have to tell whether it's real or it's a morphed image. Now it could also be deepfake, right? You can generalize it for deepfake system. And in the other one, you have to some airports in I think in Bangalore, Delhi, and in Hyderabad. You see that there is a small gate, Digiyatra. How many of you use Digiyatra? Some of you should have used Digiyatra, right? There is a camera that is in front of the gate, and that is a picture, and then it compares it against the picture that is in your Aadhaar card, in your tax card, or in your passport, right? So then in that case, I have a reference image. So you can now detect based on the information from reference image versus the image that is present in the past or ID card. Okay? So that is what is typically called as differential morphing attack detection. So the goal is then to say whether it's real one, bona fide, or it's morph. If it is bona fide, then I send it further down to the second intent system. If it is morph, I reject it and I say, okay, there is something suspicious. So here is a sample that one of the students created with his photo and my picture. And you see that here the ethnicity is very similar. He's from Nepal and I'm from India. And then this works quite okay, right? So the skin colors match and the textures match and so on. Now, with the diffusion-based approach, with the L09-based approach, what he also did is he took the output of that image and then he said, okay, make him look a bit more realistic. And now you suddenly see that there are so many spots that are coming here, the dark spots, which are not present in my regular face image, right? Neither in his face. So the idea here is that you take a base technique and then you create a morphed image and then you can fine tune it using LLMs. Now, at this point of time, you should also be a bit careful about the fact that if you upload an image to the GPTs, then the data is stored there, unless you explicitly say that do not store the data. Okay? So just if you are trying to work on such approaches, take into account this privacy aspect. Okay, so why is detection a problem in this case? Now, just imagine a situation where I'm uploading a passport photo, right? So the passport photo can be printed in one camera, captured in one camera, and then it can be printed using, let's say, HP printer, and then I can scan it using Canon printer, and then I have to make a decision, right, on that image. Now, within HP printers, there are thousands of printers. Within the Canon scanner, there are thousands of scanners. Now, the combinations can be very, very big, right? So how many combinations can I send? It becomes very infinite, right? It becomes very intractable. So I cannot generate all the samples for this to create a method which can detect all such kind of attacks. So what one of our colleagues did is that he said, you know what, I have this generative adversarial network. So I know the properties of a particular scanner. I know the properties of a particular printer. I simulated that. So you take the actual images, like let's say the digital image which is here, and then you have the properties of this print and scan, and you have the properties of another pipeline. Everything can be put back, and then you generate such new samples over and over. So what this gives? This gives the capability for you to create such images without even printing and scanning. Like, it's very expensive process, right? If I ask you to print 1 million images and then again scan it, it's very tedious. So you don't want to do that. So you can use the generative adversarial network to inject such kind of characteristics into the image. Okay. This graph only shows that okay, those images that are created are very realistic and they can attack the system, as you can see here. You can see that the accuracy of the original image is 0.25, and then it's still 5%, which means 95% of the times you can succeed in attacking this. Okay. Okay. So I should not only tell you how to create the attacks, I should also tell you how to detect the attacks. So let's try to see at some samples. Again, just to recap, you have the single image based morphing attack detection. You have differential morphing attack detection, which is reference based. So one of the earlier work that we did was 2022 is that you have this unit architecture. Some of you know about this unit architecture, yeah? So encoding and decoding, right? So I encode it at different spaces and then I decode it at different spaces. The goal is whatever I give the input here should come out here, right? So there is an input, there is an output. The encoder should learn the representation from this particular image, 112 by 112 image, to something that is 512 by 7 by 7. And now if I learned everything properly, it should be able to decode everything here, and then it can get actual image as it is, right? So what can I do? So every single step, if I take a difference between them, then there is a final difference in it, right? So I take the original image and I take a difference to get one residual image, which looks something like this. How much of difference is between the actual image and the reconstructed image? If I do that, then I have a new image, and the new image can be used to learn a classifier. This could be any of your classifier, right? It could be any of your favorite classifier, transformer based or CNN based or so on. Now, in this work, what we did was also to tap into the fact that every printer and every scanner has different color representation. For instance, if you take the photo in your iPhone, it will capture different kind of red colors because the color gamut is very wide. And if you take the same photo in, let's say, iPhone which was done 10 years ago, the gamut is very different, right? So that means that has a particular characteristics of red, green, and blue. And now if you take just the red, green, and blue, you see that the number of pixels that are in this RGB channel have a certain property. They have a certain profile, right? And the original one is also very similar here. Now, if you take a morphed one, it can be in between this and this. So these two, right? So it tells that if you're just basing it on RGB information, maybe it's not very informative. So what can I do? I can convert it into a different color space. And this color space is HSV, which is hue, saturation, and value. Or I can convert it to LAB for the representation. Or I can convert it to something that's used for specifically for the media information, YCBCR, the one that we use for television these days, right? So by combining the information from this channel, this channel, this channel, and this channel, I can get 12 different residuals. Right? In each different channel, I get one residue image, and then I have, instead of banking upon one particular channel to make a decision, I'm banking upon 12 different channels. So my classifier becomes slightly better than the original was. And here is the idea of the generalization, right? What do we mean by generalization? So there are five techniques. There is one technique to create morph, technique number 3, 4, and 5. So if I train it on technique number 1, then the system is very good at detecting, right? Because it knows the kind of data it's dealing with. So I train it with approach number A, and I see the results are very, it's extremely good for same set. And then if this is trained on LMA, and if I'm testing it on LMA, it is 0%. If I'm training it on LMA and then testing it on GAN-based approach, the error rate is still around 5%, 5%, 5%. Okay. Now, if I do it with LMA and with StyleGAN, with this approach, the error rate is around 27 or 28% here. So which tells that there is still a problem of generalization. This is better than the previous approach, but still the generalization is not effective. Okay? Because the network doesn't understand different kind of data. And the challenge is more pronounced when it comes to the some kind of other approach. For instance, this is extremely good. This particular approach, if you train it on that, you get almost 0% error on this one, style game. But then it solves one problem. The other problem is still open, right? So you need to kind of create a new new approach which uses the idea. Okay, just to recap on what we're discussing so far. Here is the idea of using color space because they all give different information. So each single channel itself is not able to identify or present the information very distinctively. But if you combine all of them, you get better results. And again, the idea is also quite simple, right? You have two samples, S1 and S2. And if I'm able to reconstruct the same sample, same image, whatever the image I'm giving it, the residue should be very, very little. The actual image minus the reconstructed image in particular channel, red channel versus red channel, green versus green, and so on, it should be very close to zero. Yeah. If it is not close to zero, that means that there is something that's happening in the image which the network is not able to capture, which can be a cue to the morphing attack. It doesn't necessarily say it's a morphing attack, but it can be a cue that can be used for learning the classifier. Okay, if you read the paper, you'll find a lot more details there, but you just get the idea here. And here I just want to show you something else, going back to the ideas of what we were discussing previously in the last two classes. The center loss, which is nothing but it's kind of telling that, okay, if there's a cluster of images, all the real images lie in the same cluster compared to all the images that are not in the real space. Right? Then you can introduce a center loss. And the other problem is that you might get infinite amount of real samples, but you might not get infinite amount of fake samples. Or vice versa. If you're generating like a synthetic sample, then you can generate n number of synthetic sample mocked images, but not necessarily real images. Right? Maybe we have, let's just take an example of this class, right? So we are approximately around 40 people here. So if I do a combination, the first one with second one, first one with third one, first one with fourth one, I can generate n number of samples, but the real samples are only 40. So there is an imbalance between two classes. So we made use of asymmetric loss, which is accounting for the fact that, okay, there are some positive samples, but there are a very high number of negative samples. Yeah? By putting that, you can improve the approach slightly. And then there is also the triplet mining that you already know from face recognition. So similar page should remain in the same space, but samples that are far away, they should remain further away. So then you can make a triangle out of them and say two points which are closer will be having lesser distance as compared to the two other points which are farther distance. Yeah. And then since we are introducing this different channels like red, green, blue, and so on, I can also see how much it is deviating from each channel individually. So then I can combine all of them together to get an averaged information in this case. Right? Okay, so this is one way you can learn the morphing attack detection.
That when we use central loss, it will be accuracy or just it will separate the two samples.
It will separate the two samples.
It will not increase the accuracy of
It will increase the accuracy, right? Because you're putting all the losses together. So what is your final loss? Your final loss is nothing but LC plus ASL plus LT plus LR with some lambda factors, right? So you weight them differently. You just say it's a total loss function. It's nothing but a combination of all these four losses.
What was the idea behind using these pair of clusters?
So in the paper, we show the combination of different losses. But here the idea is that since it is clusters, so I can use this cluster loss, center loss. And because it's imbalanced, so I need to deal with the imbalance. So I introduce that loss. And triplet mining because we are talking about identity information. And then we have the channel resolution because I'm doing 12 different channels, RGB, HSV, LAP, and so on. So you can also plug in more sophisticated methods. Okay, so I'll not talk about this one, but also to give you some ideas about this visualization approach and the visualization. So class activation master, if you will see in some time, we'll start with the deepfake soon. So here you see that all the cams that we have been talking about, so they are very inconsistent. So they help you to make understand okay, what is happening inside the network, but they're still very inconsistent, right? So in the first case, so this is the real image. This is the real image. And now when I come to this part, it shows that for this real image, I'm using the region around the eyebrow and the region in the head to tell that it is a real image. But then when it goes down here, it tells, okay, to detect it as a morph, I'm using completely different information. Right? So it means that it's not banking upon same information as you can see here in a detailed manner. So the bona fide image, I know that nothing has been manipulated. So it is quite good. It shows, okay, I do not see any manipulation here. But then when it comes to the other side, it also says that I think this is a real image because I have high activations in this eyebrow region. Right? And then if you take the attack, which is in the bottom side, you can see that the information that is here is different, and the information in the nose region, this is good because this is the region that is manipulated, but then it's not consistent, right? For instance, if you just ignore all those things, right? Let's just assume the other part. Take a look at this one. So it is looking at the chin area, it is looking at the hair region, it is looking at the background region. So if I'm telling somebody that, okay, I think your face image is small because of the background, then it's also not good, right? So I cannot explain it to somebody who's trying to get a passport. Okay, so this is an area which is also very underexplored. So if you are interested in working on this, it might be very nice contributions to the field. Okay, so this is reference-based approach, and then you can also do you can more or less take the same kind of approaches and then you can learn it in a reference-based scenario. So what do I mean by reference-based scenario? I can extract the embeddings from two images, and since I have two images, I can take a difference between them, right? If I take a difference between them, then I can learn any kind of classifier. So the classifier could be SVM, it could be linear regression, whatever the one that you like, you can plug it in there. Okay, so here it shows some different samples on how it works, and here you can look at the modularity, right? In the modular scenario, you can use ArcFace, you can use MacFace. Tomorrow, if there is a better system that is coming out, you can also plug that one in back. Okay, it gives a modular approach for that. Okay, now you might be questioning me, right? You might tell that, okay, it's all nice and good, but the governments in Europe will not let me use their data sets. So what can we do? It will be the same in India, right? Maybe MP government will not share it with Karnataka, it will not share it with Delhi. So how do we solve this problem? So there comes the idea of using the federated learning. So the idea of federated learning is that you are learning models independently, but then one model gets uploaded. So I learn a model in Jabalpur, and then this is my model number one. Here, now I don't have to share the data with somebody else. I will ask, okay, Indore also to do the same thing. I will ask Gwalior also to do the same thing. And each of them have their own model. I ask them to share only their models. Right? So when they share the models, I can upgrade the weights in a global model. Right? So by combining all these ideas, then you solve the idea of the problem of privacy. I don't have to care about privacy anymore because I'm not really giving out the data. And then you could also, if you're in a lucky situation, what you can do is you can do this, right? You can combine all the site information, different sites, and then put it into one data set and then learn it. But it's very expensive. So what you can do is you can go for this kind of federated learning approaches. And then within the federated learning approaches, what you're doing is you're just updating the weights. You're not exchanging them. Yeah? So this is another area that you can look at. I will leave it at this point of time because these are some recent works that are being done. Not too many works are again here in this area. So you can You can take this as an active research area if you want to, especially those of you who are studying this security aspects and then if you're learning the privacy aspects, then this could be a very nice idea to explore further. Okay, all these things that we have discussed so far, right? They're also kind of usable in deepfake detection because I told you like morph is a subcategory of deepfake, right? So all the techniques that you do here will be usable there, and vice versa. Everything that you develop for deepfake can also be used here. Or you can say, okay, I treat both of the attacks as one attack, and then learn one model which is applicable for both of them. Okay, so any questions on this part?
Like we saw those class activation maps.
Yeah.
And then we know like which part the model is focusing on and everything. So how can we use those maps to improve the model?
So that's a very interesting question. So I have it in the demo today. I will show you later how you can use it. Let's say, for instance, this one, right? Okay, this is the image that I generated today morning for the demo today, later. Now, as soon as you look into this image, right, you see that it's very inconsistent. Now, what I can ask is, I can ask, I know that 10 of you are very good at detecting these images, and then I can ask you to annotate this. And if I ask you to annotate this, and then your annotation is very similar to this one, then I can merge those two. Then I can use it as the attention mechanism.
Yeah.
You remember the attention that you force in the transformers? What is attention? Then I'm forcing the network to learn something very specific. But to learn very specific, I need to be very sure that that data is good. How do I do that? I extract it from the network and then I can train a network to look at the places where humans are looking at. And now when I'm saying humans are looking at, I want to also make sure that those humans are very good at detecting this. If my error rate is 80%, maybe I'm not the best one to mark the image, right? But then we have some trained experts who are extremely good. Maybe I can show some examples tomorrow. So they have nearly an accuracy of 100%. So those people, if I ask them, well, okay, why did you think that this image was small? Maybe they will say, okay, look into the eye region, look into the nose region, mouth region, and they can mark those areas. And the areas that are marked, I can use it back in the training. I can take that and then tell, okay, to the network, only look into these areas. Do not focus on the entire thing. Yeah. So that is human aspect is also very interesting aspect that people have been studying in the recent years. So we have some works. I don't know if I'll be able to manage to show all those things, but I'll try to show it at least tomorrow. Okay, good. So now I don't think I have to repeat this again, but you understand the idea of the deepfake, right? So then we can just go back to this generation approaches, and then we kind of realize that there are different variants of the networks for the GAN, orbited cycle GAN or style GAN based deepfake creation. All these attacks need to be detected, right? So how do I detect that attack? And I also showed that we also looked at the comparison scores. We saw that the comparison scores go up when I created the fake sample, synthetic sample of 2 images, the one that we did on Friday or Saturday. So what do we need to do? Again, we need to detect them, right? So let's start looking at the detection approaches. I'll give you some examples of how we can detect them and what is good, what is bad, and where we can improve the systems as our contributions for future on. So if you look at the first set of deepfakes, right? In the very first set, you see that the images are not of very high quality. On the left side, you have real images. On the right side, you have the fake images. The moment I show you this image, you will look very closely into the eye and tell there is something wrong with this image. This is a deep, right? So you can train a classifier which identifies such anomalies. For instance, here in the nose region, you see suddenly there is something double nostrils appearing. which is also the same problem in morphing, right? You get the double edges in the nostrils. And then look at this other one, the teeth that has a particular texture, particular structure, is very smooth in this case, right? So if I know these artifacts, I can train a classifier which can detect them. Right? So what can you do? You can simply take the eye region, take the regions of all those blocks and then train a classifier. And now let's go back to one other approach, right? If you think that, okay, deepfake can be improved and I don't want to use all those features, you can simply look at the way the eye blinks, the way the lip moves, right? We spoke about that one last time. And here you see that each sequence, each frame that I'm getting, if I take one particular region of the eye and then I simply model it as a sequence because it's a continuous signal, right? It's a video, which means I'm getting sequence continuously. And there should be some kind of continuity. And if I'm using LSTM, I can say on this image, I can make a prediction. I can say that, okay, this is not a deepfake. And then in the next one, I see something else. Next one, I see something else. And by sequencing them continuously, I can say at this point of time, I'm very sure that this is a deepfake. Right? So I can make the information from all different ways to come up with a list. So typically what happens is that you have one frame, but in many cases you can have multiple frames because in 1 second you get at least 24 frames. So if I capture an image for 1 second, I have 24 frames where I can make use of all these approaches. Okay, so what is the problem? So I also showed you very good deepfake recently that were created. If you create it using the GAN approaches or with the diffusion approaches, these problems get eliminated, which means that it's not really used. Yeah? But at the same time, do not ignore this fact because you might still be challenged with some old school deepfakes. Right? So you do not know what kind of attack you're getting. You're getting some new attacks or you're getting new attacks. So it's still an important feature that you can use in your deepfake detection. Now, last time I showed you the FS scan, and I showed you in the FS scan, you are looking at the landmarks. And then by using the landmarks, you can swap them. Why can't I invert the same idea? I have the landmarks, and if the image is not manipulated, the landmark should not be shifted too much. Right? So they should be lying in the same neighborhood. It should be plus or minus some x distance, and I can use that information. So here you see that there is a actual person, and then there is the face detection, and then there is the landmark detection, and then you have the landmarks here, and then I get another landmark for different person, which is a manipulated image, and the landmark of this and this should be close vicinity. X1 minus x2 should be close to, let's say, a delta. Right? So by doing this idea, you can achieve very good accuracy. But then the problem is that not everybody is going to be giving the face image in the frontal line. Right? So if I have completely different pose like this, the number of landmarks that you're getting is very, very limited. Okay? So it is good, but it also fails in certain cases. Okay, so what do we do next? Proceeding from there, we have the idea of this transforms, which is x1 minus x2, which is simply a affine transformation. Now, if I can put affine transformation into a bigger network, you can also say that, okay, there could be some blur in the deepfakes. So now I have the idea of key points plus the image characteristics. So as soon as I have the image characteristics and the key points, I can train a network, right? Because now I'm not constrained with looking for particular information, but I'm looking for the whole image information, whole face information. So here they showed a couple of different works in that work where they showed if you have an image like this with two-string neural network, you get some accuracy around 85%. But with this approach, they could bump the numbers up to 97%. Right? And remember again, the idea is that this is all new, right? How they are treating the information. But this one itself, the network itself, is any kind of network. It could be VGG, it could be ResNet, it could be ResNet 101, and so on. Right? The idea here is to make existing networks, but add additional steps to that so that it becomes better. Okay, and then mouth region. So I showed you in the first image, you have this nice dental structure that you can capture in real images. But as soon as you go to the fake images, you see that they're very smooth. So if I know that the information is very smooth, now you can already think about any kind of approach that you want to use where you simplify it out using trivial decoding. Again, the problem is that it fails with new generation schemes because new generation schemes are very, very strong in terms of information, in terms of generation. Okay, what about color? I told you in the previous case, in the gun, we had these spots that were coming up, right? And the color also could be unrealistic sometimes. It could be some person who's, let's say for an Indian ethnicity, if the image generated is in Caucasian color, then we are very sure that, okay, maybe this is not really the real image. So I can look at the color information. So here is the idea of looking at the color information by scanning the line. So you scan the whole line and look at the pixels, and you scan the next line, look at the pixels, scan the next line, and so on. You can do it also in this way, right? So if you do it, you kind of get a nice signature like this that you're seeing on the top. It's nothing but the color information, which is encoded slightly different. So then you can say you can train a classifier which detects the real colors, the natural colors versus the colors that are unmatched, right? Which is what we did in the case of morphing attack detection. We looked at the color of each different color, and then we learned the class. So here, instead of doing multi-channel, they show that you can still use this approach. But the problem here is that it is very low performance, right? Because the color can be changed due to just lighting. It can be changed due to the angle of caster. So all those factors will impact this performance. Okay, so what can we do? So now comes the idea of using different color spaces. Instead of just using one color, RGB or red color alone, I can use red color, green color, blue color. Or in a different channel, I can use HSV, the hue saturation value. And if I try to look at the distance between each of them, and if I try to look at the distance between the correlation between each of these channels, then it will also give me a feature space which I can use for learning the classifier. Right? Okay. At this point of time, this was work that was published in 2019, and then you can say that I don't want to do so many things. What I want to do is very simple. I just take the different color channels and then try to find the residuals. The residuals is nothing but the original image minus the channel image. And for each of them, you can create this kind of vectors, feature vectors. And then once you add feature vectors, you are very free to choose your own classifier, whichever is your favorite, whichever is performing better. And then you can say that, okay, it's real image or fake image. Yeah. Okay, and then comes the idea of fingerprinting. So what is the idea of fingerprinting in this case? So if I have an image and if it is creating another fake image from that, the generation schemes will always leave some kind of traces. In the GAN, we saw that there were some spots coming up. So this is nothing but a fingerprint that is unique to that particular scheme, right? So if I understand what is the fingerprint that is left behind, what is the feature that is left behind, then I can train a classifier on that, right? So here you can see that the work done by some of the colleagues in Netherlands. So they showed that if I have a video, which is also unconstrained, but if I know the generation scheme, then I can create a classifier. So the goal here is that take the whole video and then crop them into number of frames and say, okay, this is the group 1, group 2, group 3, and then you can use it for detecting the attack. And here there is also another interesting aspect that we should discuss. For most of you who, is there anybody who has done signal processing, cameras, image processing? You did image processing, yeah? For those of you who have not done it, just as a tip, every camera that we use today will have its own sensor noise. So the camera that I have and the camera that you have will have a different unique signature. Right? If I understand the signature between the camera sensors, then anything that is generated will be very different from that signature. And this is what we call it as PRNU, which is photo responsivity, no, photo response non-uniformity. Right? It is like if I just flash a white light onto the camera, it captures an image and it gives me the signature of that sensor. Right? So that means if it is not real, then the signature of that particular image or particular video will be very different from what you will capture from real cameras. Okay, so PRNU is another aspect that you can look into. Then comes the idea of Fourier transform. So we started with thinking about the color information. Now we can also think about the frequency information. If it's a real image, if I take the Fourier transform of that image, then I get a very different signature as compared to the signature that I would get when it is a deepfake image. Again, the idea is that the signal is artificially induced, right? So as soon as the signal is artificially induced, then the kind of the Fourier transform that you're getting here will be very different. Okay. Okay, so what can I do with this one? If I know that kind of signature exists, which is very different, I can simply take it back and then learn a classifier. Now, how do I learn the classifier? Take a DFT, and then if you take the DFT, you get a spectrum, amplitude spectrum. And then from that, you take an average of them in a particular angle, in a azimuth direction or in a horizontal direction. And then once I have the spectrum, then I can say if it is a real or a fake image. Right? So on the bottom side, you see that how the spectrum of the images change. And here you see that the threshold of the real ones are much higher as compared to the threshold of the fake ones. The fake ones are generally lower, right, in the spatial frequency. Okay, do I need to really go back to this this kind of classical processing? Can I not do any deep learning? There are a number of works that I've discussed deep learning based system. One of the classical approaches, you take existing CNN, you put in the images, you put them into two different bins, and then you learn a classifier. Then it says, instead of learning it as cat or dog, what it does, it just learns fake or real, which is what we will see in the exercise part later today. Okay, and then you have, since you have the video, I could also make use of the time. The consecutive frame that I have, they should have very similar characteristics. If the characteristics is changing from feature number, the frame number 1 to frame number 5, then that's a likelihood that there's a likelihood that it's a fake image. Yeah. So what can I do? I take the CNN to extract the features, and once I extract the features, it is, let's say, 30 frames. I have 30 different features, and from these 30 different features, I can learn a continuous signal processing using long short-term memory networks. But then it becomes like a speech, right? It becomes a continuous waveform, and the continuity should be very similar in the case of real as compared to the fake. Okay, so that gives you an idea. And then here they also showed that if you use just 20 frames, your accuracy is around 96%, or test accuracy is around 96%. But if you use more number of frames, then the accuracy improves. For the 80 frames, it becomes 97.1, right? So the more number of frames you have, the more the better the system becomes. At the same time, you should also consider one other aspect. If you ask somebody to take a video for 5 minutes, they will not be very happy, right? If you ask somebody to check the bank account and then log into the phone, and you ask, okay, wait for 5 minutes, I need to verify your system, your face image as real or fake, then people will not be very happy. So your system should be optimized in a way that it takes minimal number of frames, but still make a better use. Okay. Then there is also this Mesonet, which was also proposed in 2018. Here, what they are doing is that they are taking the mean output of all the fakes and all the reals, and you see the response maps are very different. So for this one, it's very strong in the left part and it's weak in this part, right? Right. So if you can also identify these kind of features which are very relevant, then you can also create a new network which is good for deepfake detection. Again, these are all like a bit older networks, so most recent networks have better capability. But the main idea why I wanted to show you this is that you don't necessarily have to create the whole new architecture. You can use existing architectures, you can reproduce. Right?
So
Yeah.
what compression factor is used in the deepfake?
In this case, okay, that's a very interesting aspect I did not discuss on the other day. What is the compression factor? For instance, if you upload it to YouTube, your compression factor is, I think it's a set called as C23, which is standard compression factor for YouTube. Now, you might train your system on very high quality images, but they might start failing on the low quality images, which has compression rate. And the compression rate is also very different for different vendors. WhatsApp uses its own compression mechanism. Facebook has its own. But if you are using, let's say, Zoom, it has its own compression mechanism. So you'll have to study all these compression factors and then show that it actually performs quite well across different compression factors. Okay? So this is a very hard question to answer because you do not know which kind of compression is used internally.
I have explained in that slide.
In the previous slide?
Yeah, in the deepfake, which compression factor is used? On the basis you have given the accuracy. Yeah, in the
In the accuracy part. Yeah, here you see C23. So this is the deepfake. This is the standard data set that we will use for today for the examples. And then you have subsets which is called face to face, face up, and so on. And each of them in the original data set is given with the compression factor. That is called C23 data set. Right? The subset of that one with that standard YouTube compression factor. Okay. But as a tip, if you are studying, just study all the different compression factors if possible, right? At least the most common used one, JPEG compression factors with the 80, 60, and 20, and so on. And also the one that is used in videos. Okay. Then you get an idea now, right? You get, if you have video, you can also, you don't necessarily have to do it as sequentially, but you can also do it parallelly. So every single frame you take, you pass it through a CNN, and then you kind of learn a recurrent neural network, which is processing the time domain. So what benefit does it give in case of the recurrent strategy? So if I have the actual image, and then if I have this, let's say, you can plug in different things, right? In this case, here is a color domain, and there is a frequency domain, and each of them should be continuous, whether it's color domain or the frequency domain. So if I have these two channels, then I can fuse the information. So I can make it a multimodal system by looking at complementary information which is not existing in one of them. And then they also show some visualization how it actually identifies and localizes. If you look very closely into this image, you probably will see that there is the double eyebrow here. And also the lip is very different, and which is what is captured in those images, right? So here this is capturing the lip information, the frequency is capturing the eyebrow information. So you see that by fusing the information from complementary domains, we can make the systems better. Okay, now should we just forget all the classical machine learning? No, we do not really have to forget that. So what we can do is, if I have multiple information from different components, then I can also fuse them using a weighted strategy. Right, so it's a simple processing. You simply take the features from any of these networks, like RSpace or with efficient net and so on, and then you combine them as independent components using a fusion. Okay, so here comes the attention mechanism. So in 2021, the paper was published, and here the idea is that you have some image, and then you want to tell the network to focus on specific areas. Right? So how do we do it? So we have this simple processing which is going on the bottom part. It's like layers, and so on, and then you have a classifier here. And before the classifier comes into action, what I'm doing is I'm also introducing the attention. And now this attention could be as simple as telling the network to focus on your eye region. or the class activation maps that we looked at, I can say, okay, multiply the image with a class activation map, and then only these areas will be activated. Okay? And then I have a better classifier on that. Now at the same time, I also mentioned about this texture, right? So the information that is presented in the real image will be very different from the fake image. So that means the texture is different. Right? What do we mean by texture? The skin appearance will be different. And then maybe the lighting will be different. So all those information, if I have that, I could also create one more block on the top, which extracts the similar information. And then I make sure that this becomes the attention mechanism. Right? So it could be modern day systems are even better there where they're saying, okay, they're also describing the image. So that doesn't have to be the attention maps purely derived from the image, but it could also be attention given by text input. Right? So you can also describe the image telling that, okay, the image looks suspicious on the eye region, and then you pass it to the network, and the network learns this from the image text mapping.
Can we make such attention layer which will only pay attention on eyes particular?
Yes.
Particular part. Can we do that?
You can do that. So this is where the attention maps are coming, right?
Okay,
So,
maps.
yeah. So the attention maps are coming, and then you can say you would simply take the image and then you mask all the other areas, and then you say only activate the eye region, and the information that will be used here, learned here, will be only the
Maps are pre-trained or pre-learned one.
You can either pre-learn it, or in this case, they're learning it from the texture itself, right? So here they're learning it internally by looking at the texture discrepancies.
So we can directly crop that in password.
You can directly crop that at password. Yeah. So that is what I do, right? The model number one is that you forget about all these things. You say, okay, for every single image, you create the annotation of ground truth using the CAM maps and then pass it in. But now also remember, creating such maps is very expensive.
Exactly.
If you have 1 million images, you have to be very sure that which areas are manipulated, right? And this is complicated process. It takes a lot of time to create such map. So what they do internally, they try to learn it from their own. Yeah. But that is a very interesting aspect because the only thing is that the manpower requirement is too high. So in this case, you see that it's
If we just make a mask for eyes,
Hmm.
will it qualify for an attention layer?
It will qualify as an attention mechanism. So you are enforcing it, right?
Just creating a mask.
Yes. It is one way of attention. So, but it's a simple way of attention, but you can make it more complicated, right? More advanced.
But
also.
don't know where eyes are present. We
Exactly.
are taking into account that face will be always in this position.
Front of face. So it will work in most of the situation, but in some cases it might start failing. But that is the problem with all the systems, right? It will not solve all problems. So you have to account for different settings and then use the then create the technique to take into account. Okay, so in that case, they what is good with this approach with the internal attention is that they could identify and say that, okay, look, this area is manipulated, high activation region, and this area, the mouth area is manipulated, right? So in all of them consistently they could show it.
Till now, we have seen only CNN-based placement.
Yeah.
Ways to cut, it's only real transformer also being
Yes.
multi-rated and cross-rated, and maybe some computers also.
Yes, very important point. Going back to your question, right? So the idea here is that in the vision transformers, we have this ability called as multi-rate attention. Right? Now each of the head could be different thing. One head could be telling that, okay, focus on the eye region, second head could be telling focus on the nose region, third one could be telling focus on the mouth region and so on, right? So then you have multi-area attention.
Also, it can globally identify the wish feature, which is different.
Yes. It can also, so the advantage with transformers is that it's global attention. So the CNNs is local attention, right? So here you see very specifically that the attention is spread in this area. But in the case of vision transformers, you can try to identify the global structures of the global information as well.
This is not that much work done using the vision transformer.
So there are some works done in the vision transformers, but there is still like this open challenge of generalization. Right? Generalization is open problem, and then there is also the video based detection. Video bit.
Will also be good for the.
Yes.
So time frame data can very good.
You can get very good information from the time information, but not too many works are done. So CNN, it's too many works are done, but in vision transformers, it's a handful of works, but they're all very good so far. But you can certainly explore that area. If you are planning to explore that area, what I would also recommend is to look at this multimodal information.
Okay.
So in the sense,
Multiple.
so the information can be from text and the video and the audio.
Yes.
Right? Audio, text, and video, both, all the three. Okay, so just before I go to the demo part, I just want to also show some other physiological signal based. Maybe some of you are coming from strong signal processing background, you do not want to do deep learning, and in that case, you can clearly see there are some approaches which are applicable here. For instance, if you look at the forehead region, and if you try to look at the information that is in the forehead region, the color that appears in the top part and the color that appears on the bottom part on the right hand side is very different, right? Left hand side, right hand side. So, and then if you have this information, you can draw a signal out of that. It's nothing but a continuous signal, right? So for each pixel, the values go up and down, up and down. And here you see that for the sequence of frames for the same pixel that you're measuring across all different frames, the signals are very different. So you have the real signals, which are in green, and then you have the red signals, which are in the different area. Okay? So simply by looking at the flow of the blood, your flow of the blood is what creates the color on the face, right? So if you are able to say that, okay, in the fake ones, it's not really following that area, following that pattern, you can tell it as a faking. Okay. Okay, and then also there's the motion of head, right? So the head will move in a certain direction. It cannot go from left side to all the way to the right side, right? There is a transition between them. And there is between the transition, the motion is also following a particular pattern. Now this is again physics based, and then you can model that one. And when the motion is happening, there is also the appearance factor that changes. If the light is falling on my face, then the face changes slowly to the left to right. The lightness to the darkness becomes very transitional. It's not abrupt transition. So if I can model that one, then I can also create the models which can that kind of attacks. Again, the signal-based system, this could also be like the heart rate, right? So here the idea is that if you're able to first identify the heart rate, you'll not be able to get it as a gold standard, the one that you get in the hospitals, but you'll be able to approximately identify that. So the patterns that you're getting should follow the standard pattern. If they're not following the standard pattern, then you can tell that, okay, the system, the image is fake. And also, remember the across the frames, the distance can vary. See, in some of them, it's telling that, okay, it's a score of 1, it's likely deepfake, and then it goes all the way to drop to 0 as the time passes. Every second is nothing but 24 frames. In 24 frames, you can see some distance are real, some distance are fake. Yeah? So this it's again a problem that you face when you're deploying the systems. Okay, and now if you tell that, okay, well, the forehead is not really very good because maybe I have a forehead which is very constant, but the other components are edited, manipulated. So what can I do? I take the whole image and then chunk it into different blocks. Again, multiple components, and for each of these multiple component, I can establish this PPG signals. PPG signals are typically the signals. What is it called? Plethysmography, which is another mechanism which is used in medical applications. Right, your blood pulse.
Heart rate sensor.
Yes, blood pulse first. Blood pulse, yeah. So that is again, you can put on the device onto the fingerprint or on a finger and then measure that. But since we are dealing with videos, we will not be able to do that. So what can we do? We can estimate them. Right? So every time I estimate them, I can learn a classifier. So then there should be some consistency. And whenever I have a consistency, there should be also the features that will be in the same space. Okay, and if I can extract this, now I can go back and learn any kind of classifier here, right? I can learn a classifier like USM based, likelihood based, or any of your. If you don't like that, you can take the. You can convert this into images, which is like a spectrogram images, and then from spectrogram images, you can learn a CNN based classifier. Right now, it doesn't have to be CNN. You can also plug in a transform object classifier. Okay. Okay, so then there was this another work which was came out in 2020. So the idea here is that you model the face as a 3D object. And then if I model the face as a 3D object, it's in a certain volume, right? So the object that I consider here, it will be in a certain volume, and the volume cannot change very abruptly. So then you can estimate the gaze angle, for instance, here you see, right? So now suddenly in the deepfake, you have two different faces which are coming in between the frame transitions. And this transition will tell you that, okay, the cube is not respecting the physics. Okay, so then you can go back and then model and classify that. This is again purely based on the video settings. Okay, and then we can go for this classical ML, right? So in the classical ML, I just wanted to tell you that I'll not get deeper into this, but the idea here is that those of you who have read this key point landmark based detections, which is used in SIFT and SERT, those kind of approaches, you get a number of orientation fields. The orientation fields which we also looked in the fingerprints, right? So if I have that orientation field, then I can also learn a vector, get a vector, and from the vector I can learn a classifier. Right? So in the classical sense, it can be used. Most of you might not be using these classical methods, but the idea here is to tell you that it's still possible to do that, but you will not get the same accuracy as you would get with the modern deep learning system. Okay, but then simply do not ignore the classical aspect as well. Maybe some of the reviewers might ask you to run some experiments on the classical methods. Then you have an idea that, okay, these are all the existing methods that can be used. Okay, before I go to the demo part, I also want to show you some open problems. Open problems in the sense that you have this generalization issue. What is generalization issue is that if I have a network which I've learned with known features, known images, the error rate which is at 3.33% here, and if I'm taking the same training model and then I'm trying to put it on a model which is completely unseen, then I see that the error rate goes up by 46%. Okay? So the idea is to not focus on the numbers, but get the idea that the error rate increases exponentially, very significantly, right? So which means all the systems that are trained and developed and shown to you will be non-usable if I take it to the real world scenario. Okay? So because the data is very different. So what has been done in the recent years? In one of the works that was done at our department, the PhD and the masters. So she took this problem of generalization, and then she modeled it as a contrastive learning. So what is contrastive learning? If I have two samples, apple and apple, and then I have two other samples, apple and banana. So I know that the difference between the apple and apple is nickel, and the difference between apple and banana is, right? So what was done in this case is that she took a bunch of images and then she augmented them in a random manner. All the augmentation, if it is real, will be in the similar domain. If it is fake, it will be in a different domain. Right? Now, at this point of time, you have this encoder, which is sharing the weights across all of them. And with that one, you can say this representation gives me some intermediate representation, which is a vector. And the same thing from all of these. Because I know that these two are similar from the same pair, you have to maximize the similarity. And because these two are different pair, I need to minimize the similarity. And then again, between them, I have to maximize the similarity, right? So it is contrastively telling apple and apple, make it better. Banana and banana, make it better. Apple and banana, between these two, increase the difference, right? So you are kind of enforcing those rules. By enforcing those rules, what you can do is that you can learn this contrast learning mechanism for deepfake detection. So by doing that one, she could achieve better results, and you see it here. If it is trained on, it's one of the existing network. The network is not new, and also the contrast learning was something that was proposed by Google some years ago. That is the base architecture. And here you see that if you train it on one of the data set and then test it on different data set, you see the error rates actually quite shoot up. The accuracies, if you're training it on DF data set, and then if you're testing it on the other data sets, the accuracy is kind of dropping slowly, right? Yeah, but it solves the same problem. At the same time, it also improves the system for the other systems. Now, if I also have this information, if I have multiple networks, why can't I also do the fusion? I can also do a fusion, right? I can learn it from one network and then I can put it onto the, I can learn two networks and then extract the complementary information and then I can start fusing them for learning. Okay. So it goes back to the idea of using the fused information. There was this other word which is also quite nice and interesting in the sense that they modeled it as a few shot problem, which means if you have a latent space which is for the source domain, and from the source domain you learn a classifier which has this kind of two different clusters, and then if I take that one and then simply put it on a pre-trained encoder, I get a image space which is slightly mixed up, then I can fine tune that pattern. So what does this mean? This means that if I have data from Jabalpur, I take a data from Jabalpur and then I test it on Indore, and then in Indore data set I see there is only small variations, and then I can always fine tune it without retraining the whole thing, right? So you're bringing the ideas of both transfer learning and zero shot. Because when I put it in Indore, then that system doesn't have any idea of Indore. But then as soon as I see the data, I can fine tune it back again, right? Then you can also have this, instead of few shot, you can have zero shot, and then you can have few shot, and then you can have multi-shot learning. Anyway, the idea here is that with the supervised contrastive learning, you see that the results goes to 78%, which is still not beating the other networks. And then by fusing the information from different sets, you can achieve better performance, right? And here also you see the same thing, right? If you have FS plus F2F plus FS plus NT, I am using three different kind of data sets to train. And then if I'm testing on unknown data set, I see that the accuracy is around 78% and the general accuracy increases because this has seen 1, 2, 3 different kind of data set. The more diverse data set it sees, the better the system becomes. So it is now 78% here. Then there is an open problem with the neural textures, which we will see today later. Whatever you do, the accuracy remains dangles between 50-60%. It's not improving very much at all. There is a different family of attacks. Again, to motivate you all again for the explainability part. If you look at this explainability part here, you see that the network is showing something. For instance, the exception network is focusing on the regions in the face area, right? Most of the images. But the supervised contrastive learning is spreading the attention also across the area, so around the face area. So this also kind of gives you an idea that, okay, maybe these two networks are taking some complementary information which can be fused. Right? So I use this visualization tool to motivate the problem of fusion. Then I have a reasoning telling that why I can fuse the complementary. And here you see by fusing them, the accuracy increases. This is 78%, this is 82%. Now by fusing these two information, I'm getting 83%. It's not massive improvement, but it still gives you some improvement, and which is also relevant in the case of real world deployment. You don't want to let at least one person to get in. So if you're able to stop that 1%, then your system is better. Okay, and then what happens to the explainability part? I am not sure how many of you know about this Disney plots and view maps. Some of you know.
It's like
Yeah, so the idea is to reduce the dimension and visualize it. So I'll briefly tell about this before I start talking about this graph here. So assume that you have two deep networks, and the deep networks gives you the features of, let's say, 512. Now I cannot see 512 classes, 512 features in the same space, right? So what can I do? I take the 512 features and I can learn a principal component of that for the entire matrix. Now, if I learn the principal components of that, I can say set it to 2. And now I have two features, and then I can project them back. So on a 2xy matrix, I can show where the features are. If you do it for, and there is also this manifold approach, which is very similar to what I discussed now. And there you see that the features of fake and real are so much mixed up. So which does, okay, there is some way that I can separate them, but I can't really separate them very well. But also for this exception net, you see that it's clustered very well for one class, and the other class is also very spread everywhere. And now these images are also spread somewhere here, right? So that means you have a mix up of both kind of features. And by getting to the fusion, you at least improve this mix up here. So now here you see that the blue ones are clustering closer and the red ones are clustering a bit far away. Okay, so this is one way of looking at the feature space. And then before I go here, I don't know how much more time I have. I have some time. At least I'll show you some other problems. This you can take a look at the slides. And then we also looked at another approach which is called as the similar architecture, which is called as pairwise interaction. In the previous case, I talked about this the contrastive learning, right? I showed apple, 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 banana. And here in this case, it's like you try to find the interaction with that. How much do apples and apples interact? How much do apples and bananas interact? By looking at this, I can have 4 features, right? Apple, 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 banana, 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 apple. 4 interactions. So by looking at this 4 interaction, if I model them and then try to learn a plot, try to learn a detection mechanism, here you see that if you are using a simple architecture, the clusters are like this. So the clusters of one of the kind of the deep fakes and the real ones are all here. The fake samples are here. The face swap is here. The F2F face-to-face is here. Neural texture is here. And now, if I'm just extending the idea for multiple channels, in the multiple channel, what do I mean by multiple channel? It can be RGB, FSV, LAD, color space, or information, frequency information, and the temporal information, spatial information. Then you have better separation. So the better separation can be seen here, right? You see all the green lines here. Now the green lines are pushed further away. And the same thing for the this part. So the combination here, the blue and the pink ones are overlapping, so they're better classified here, so they're better distributed, right? So Disney and UMAP are some of the other alternative mechanisms, but then you can also do the same analysis using the class activation map. So if you do the same with class activation maps, again you see that the actual base architecture is focusing on the nose area, which is good, and then it's focusing heavily on the hair region. While if you use multiple channels, it's focusing completely on the internal phase structure. Oh, sorry, internal phase structure. Here's an idea. Okay, so there are like multiple problems that are very open, right? For those of you looking for your thesis. Okay, so this is the contrastive learning, and this is the. Okay, I'll not talk about this one. This you can take a look at it later. But I want to show you one other small thing. Let's go back to that. Okay, so just to summarize, right? Before we go to the practical part, this is the whole idea of generalization. So you have the known attacks on which I train the models, and then once I train the model, I get very good accuracy in a closed setup. And then if the moment I introduce some kind of unknown attack, and then the model starts failing. Right? So that is what we will look in the exercise as well. Now, if you do not have any questions at this point of time, we can go to the demo part in the collab or in the Okay, so in the file that you got, I think you should open that folder. Ready? So there you have this one, right? This file called as attack detection deepfake. And then there is also this demo files. Let me just open the folder. Everybody ready? Yes. So I have reorganized the data set just for the sake of using this existing architectures. And there you see that so there I have organized it as a very simple method, where I set it as three different folders. Face-to-face is one approach, which we did on Saturday. Face swap is what we did on Saturday. And then face-to-face is another approach for creating the deepfakes. And the neural texture is another approach. For each of them, I just simply made it as real deepfake, and real deepfake. Right? So class 1, class 2, class 1, class 2, right? And then in this one, so in the code, you see that it is a bit, it's a bit extensive. Let me just see if it is all properly done. Yes. So, everybody ready? You got access to the data set, right? This is the fake and the real samples. And then here I'm just setting the directory here, and I'm going to train on that. And I'm just set it as one epoch because we don't have time to run multiple epochs, just we train one epoch. And then if you train one epoch, and then I'm setting the k-folds to 0, 3. And then here you see that there are total number of 200 images, which has both face swap and the real image. And then this is the standard architecture, right? The standard architecture of transforming the images and then creating them to tensors. And then in the next part, in this block, so here I've just randomly dumped all the networks that are available today. If you run it through all of them, you will not really get any big improvement. but this to just give you an idea that you can pick and choose any kind of network that you want. Okay, so in that one, you can, in this case, I think I'm using ResNet 50. So then there are some helper code which is for visualizing the GradCam, helper code for visualizing the activations, and then overlaying them on the actual image, and so on. The overlaying is here, and then the training part is happening here. And again, remember, I'm doing it on a CPU, so I'm setting it as CPU. If you're doing it on GPU, it will be much faster. And then this is the evaluation to see how well it works. So if I run the whole data set here in 3 folds, you see the results are, in the first case, it is, so I'm using 30% for validation. So it's around 377023, which means all the real ones are classified very well, but all the fake ones got misclassified. So it's less than 20%. But then if you look at the AUC, right, it's quite high. 97, which is misleading, right? Because it doesn't show a clear picture. And then if I go for the fold number 2, so again in the fold number 2, I have the same idea. It's now getting much better. Now it became 33, 2, 28, and 33, right? So you see that now it is much more balanced. Right? And remember, at this point of time, you are training and testing on the similar kind of data set. So it's becoming better and better every time. Okay? And then in the fold number 3, again the system flips completely. Right? So what is it doing? It's taking a bunch of images and then it's splitting the whole data set into some subsets. And then it's using one set for training, other set for testing. And in the testing set, but depending on the images that are being selected, it becomes either good or bad. So if you think that you are lucky with the model and you choose this model, maybe it will work. But then remember that the moment the samples changes, it will not perform very well. It will start failing. And then also, this is a one epoch training, right? So maybe if you train it for multiple epochs, the weights are much more stable, much more robust. Okay. Good. And then now if you go to the next part, this is more interesting. So here I'm showing the generalization problem. So I'm training it based on the images from one approach, face to face, and then I'm trying to test it on neural texture. So if I do this, so the rest of the things are very standard, right? So I'm reading the data set and then I'm loading the data set, and then I'm saying that if I'm going to freeze the model, the backbone is frozen, which means pre-trained weights, and then I'm just replacing the linear classifier, because the ResNet, remember, it has been trained on multiple classes, 1000 classes, I think. Yeah. So in this case, I'm just setting it to 2 classes. And also I'm setting it to cross entropy loss, and the optimizer in my case is Adam. And then if I run this here, again, the number of epochs are still 1. So if I just run this, you can see it's deepfake and real, deepfake and real. The classes are the same. One is face swap, the other one is neural textures, I think. Now, in the epoch number 1, the accuracy of training is 57%. As we proceed, it becomes better and better. And then we will see if it works really in the generalized setting. So epoch number 2 is 83%. Also, don't be misled with the accuracy that we're seeing here, right? Because number of samples in our demo is very limited. We are using only 100 images. Okay. So in real life, you use much more images to train and test your models. So it becomes better. Epoch number 3, 88%. 91%, and epoch number 5 stops around 94% or so. Yeah, 94%. And now we are going to test it on the other data set, which the model has not seen before. Okay, now the test accuracy on the cross data set is 96%. Now, why could this be? This could be the case. I told you that cross dataset will always give you bad results, but here we are seeing a very good accuracy of 96%. Any hypothesis why it could be the case?
Samples.
Number of samples are less. Very
Very
good.
folks.
Number of epochs are also okay for this kind of data. What about the data itself? If you look at the data, are the real samples changing? The real samples are always the same, right? In all the data sets. So maybe the network is actually classifying only the real sample. So remember that these metrics, whenever you are looking at the data sets in generalization setting, even the real sample should be very different. So to run this experiment, what you can do is you can go download the whole data set. It's freely available. Just reorganize the data set as I did, and then rerun the experiments. Then you will see that the accuracy will actually drop drastically down. Okay. Okay, so let's just try to understand the other part. Let's just try to see if the CAM visualization is doing us any good. Now I'm going to use the previous model that I trained, the model which is named model. That's the same model. Okay. So I'll try to see, I have already run this overlay part. So I'll just take this one and then try to generate the class activation map. Webcam is not run, I'll run this. Then overlay cam is also not run, I'll run this. And now I'll run this one. You see the activations now? Right? So now this activation is the activation that I get for this model. Let me just save this model and also show you the consistency part. I'll put it on the drive and I say run 1. And now I'm going to retrain the model again. Take a couple of seconds. So I just want to show you that if the model changes, all the explanation of all the explanations, no, not explanations, but the visualizations also change. And also I'm showing it only on one network in this case, in the demo, but you can pick and choose whatever the network you like. You can also replace it with the transformer networks and then try to run the same code. So I think it's going to be around same 93-94% for this time as well. Okay, this time we're lucky, so we got 97%. Okay, so the test accuracy was 84% this time. Last time it was around 96%, right? So let's just try to take this model now and let's run the CAM overlay. Now remember, this is the picture that we got from previous round. Let's just run one more time. So this is the image that we're getting now, and I'm going to pull out the image from the last time. You see the inconsistency of explanations. So depending on the model that we have done, in the previous case, it was telling me that, okay, this fake image because of this area, but now it's telling it's a fake image because of this area, right? So it's inconsistent depending on the models that you're using. So what does this mean if you're going to be a police officer tomorrow, and then if you're trying to tell that I think Manvi is giving me a fake image, and then you're telling it's because of the hair region here, and next time she comes and you tell her, no, this is a fake image because of the eye region, she would not be convinced. right? So you get the idea? Okay, good. So let's also see how it varies across the real image and the fake image. If I go down here, now I'm going to simply run it for two different images. So one I've taken as the real sample, and then I've taken as a fake sample here. And let's see how it works for them. See the image now. So in the previous image that we used before, it's still okay. And the one that we are using on the right side, the attention is very, very spread. It's not even looking at the face image, it's looking at the regions below. Okay, at this point of time, I should also admit that this is not a fully trained model, right? It's a model that is with only 5 epochs and 1 epoch. So that could be one of the cause, but still you get the idea that it can be made very inconsistent. Okay, and then just to okay, I think that's the part that I wanted to show, that these are all additional samples that you can simply run. So I created also a function for making the overlay. And then here you can put any number of images, any number of output, and then you can still keep on getting these kind of images for. Again, I use GradCam in this case, but you could also use more recent ones, which are GradCam++, Ablation Cam, Score Cam, High-Res Cam. There's a bunch of cams that you can use. Okay. Questions so far? I know it's a long code that we'll not be able to walk through everything, but you can read it, and then if you have any doubts, we can discuss it tomorrow morning. And remember, the sample that I've given is only to get you started. You need to use the actual data set to get the full performance score.
What model in accuracy map, it shows where the model is focused. In GradCam, what happens?
The accuracy is the accuracy is the where the how much the model is performed, right? So GradCam is nothing but it shows which areas of the image are activated to make that decision.
If the pixel implies that there, then those pixels are matched areas or.
No pixels are matched. So what it does is, if you remember the architecture of the deep layer network, right? Deep CNN. So we have multiple layers, and the last layer before the FC, the fully connected layer, is the layer that is telling which of the areas of the image are
Those
activated.
pixel values are higher than that
Higher.
particular.
Yes. So here, the red color means that it's the areas that are contributing heavily to the decision. So here in both cases, it's telling that, okay, these areas are heavily contributing to the decision, telling that this is real image or this fake image. And this one, the red areas are contributing to tell that this is a real image. But then what is happening is also that it's telling that there is a second level of information, which is the yellow color. This is second important thing. Second important region. This is the activation, okay? In the activation, in the weight maps. Okay. Now you could also do one more thing is instead of just looking at one last layer, you can also look at multiple layers to try to see how it progresses over the period. I don't know if I have those images, but I can show you some more. Okay, anybody working on deepfakes for? I know you are working. Yeah, you are also working on deepfakes. Huh? Cool. And also, I did not mention one more sub aspect. If you are struggling to generate the training data set, so there you have the generative adversarial networks, right? Diffusion models, so it can be used for generating massive amount of training data, and then you can use it back with the training pipelines here. There is also one other method where in the training of the model for deepfake detection, they dynamically generate the deepfakes. So they send a real image, and then with the real image, they generate multiple fake samples inside the network, and they use it as positive weights and negative weights. So that is also possible. That's another idea. So every week you wake up, you'll find at least like 10 to 12 papers. So it's there is no limitation for the literature. There is abundance of literature, which is also a bad thing for you all because you have to also compete with them, right? So you have to really, if you're trying to present new methods, you have to benchmark with so many. Maybe there is another link that I can just show you. Okay, here is this is the comprehensive network, most recent and comprehensive benchmark, which is done by some of the researchers, where they list everything that is available right now. So the code is given, and the benchmark results are given along with the dataset link. So you can just download this and then try to see where you stand with respect to this big table. So here is the big table. See the table here. So they present all different approaches and all different metrics. So I can share this link as well. I don't know where to share it. I'll put it in the slide so that you have it in slides. Good. So that was all I planned for today. So tomorrow we'll discuss a bit on the privacy aspects, the security and features, and then some other aspects which are on bias. What I did not discuss today is that this training that we're doing is all on one kind of data set, right? We do not have a diversity of population. So for any method to be biased, you need to have a wide variety of inputs. You have information from male, female, younger age, older people, and then people from a different ethnicity. So all those aspects we'll take a look at it tomorrow. Okay, then I think we can do it to stop the recording now.